Welcome to Denver Startup Week. I'm Ben Data, co-chair of DSW. This year marks the 10-year anniversary of Denver Startup Week. This community has been the catalyst for lots of change over the past decade, and this week we're coming together to celebrate the past and dream big for the future. We are able to bring Denver Startup Week to this community thanks to our 2021 sponsors. Thank you to our HQ and title sponsor, Amazon, and our title sponsors, whose leadership makes this week come to life. Capital One Cafe, Downtown Denver Partnership, Fluid Truck, Hotel Engine, and WeWork. And our track sponsors, who have made all of the great content you're hearing today possible. Founder Track, Kickstart, Growth Track, Friday Health Plans, Developer Track, Quizlet, Product Track, Palantir, Designer Track, Battery 621 in the Public Works, People Track, Exactly, and Spotlight event sponsor, Strat Labs. Our headline event sponsors are bringing the excitement this week. Thank you to B-Side Fun, Colorado Public Radio, Comcast, Coors Brewing Company, Denver Pavilions, Entrepreneurship at the University of Denver, Gusto, JP Morgan Chase, Method, Moss Adams, Pine Insurance, Promontory Mortgage Path, Red Bull Basement, Southwest, Tattered Cover, and VF Venture Foundry. Finally, thank you to our partner and member sponsors listed on the screen. Please say thank you to these companies as you enjoy our hybrid Denver Startup Week. And don't forget to use hashtag DenStartupWeek to share your experience and moments of inspiration on social media. Have a great week.
Early risers, all-nighters, slow pours, fast crams, post-nap, on the mat, in the stacks, phone down, volume up, complete silence. You ups? Coffee cups, pizza crusts, first semester, fourth quarter. Focus 100, privacy 0. Pre-test, one last check, let's go. However you study, Quizlet takes the guesswork out of your coursework. Learn it, own it, Quizlet.
Hello everyone, welcome to Denver Startup Week. I'm Connor Swanson, the Developer Track co-chair along with Aaron Clark, and member of the Denver Startup Week Organizing Committee. Thank you for joining us for the 10th anniversary of Denver Startup Week. At Denver Startup Week, we strive to make all of our sessions a space where attendees can connect, learn, and grow, regardless of age, gender identity, gender expression, race, ability, or sexual orientation. A special thank you to all of our sponsors for their support in helping us to keep DSW free and accessible for all. Thank you for joining us, and have a great week.
Okay, awesome. Well, welcome to our session. I'm going to share my screen now real quick, and then we'll get started. All right. So this session is called Solving Smooth Multiplanar Reformat Image Rendering and Editing. I know it's like a real mouthful. Hopefully I can unpack that for everybody and we'll know what we're talking about by the end. My name's Nick, and in the room here with me are Tim and Vlad, two of our principal and senior engineers here at Cleerly. So before we get started, I thought I'd start by explaining a little bit about what Cleerly does, since people may or may not have heard of us. Cleerly is a company focused on detecting and preventing risk factors for coronary artery disease through non-invasive measures. That includes analysis of the blockages and buildup in your arteries through coronary CT scans. There's a lot more on the screen here, but in a nutshell, I'm trying to make sure everybody who maybe doesn't know anything about coronary artery disease has an idea of what we do. And then for myself, there we go. So who am I and who are Tim and Vlad? I thought I'd give us a little bio who each of us are. So my name is Nick Nislanik. I joined as CTO here at Cleerly earlier this year, coming over from Teladoc. I was a VP of engineering there. I have about 16 years of experience in software development, and about 7 of those years have been in varying capacities of leadership in digital health. Tim's our principal engineer. He was one of the first employees of Cleerly. He's been here for over 4 years. He has 15 years of experience. He moved to New York just recently from New Zealand, and kind of got his start 16 years ago in IBM China. And then Vlad came to New York and joined Cleerly 4 years ago. He has about 7 years of experience overall. He's from the Ukraine and is a wizard on the front end and loves solving hard problems. All right, so one more kind of piece of backstory here, just to set the stage for the technologies we're using and how we're solving some of the problems we're going to go through today. We're as you can see on the screen here, we're using a lot of common technologies. On the front end, we're using TypeScript with React and Redux, Ant Design for a design system, SAS and Webpack for their usual capacities. And then there's a couple of JavaScript frameworks I want to call out that I think are super important. The first one's Cornerstone.js. Cornerstone is allowing us to manipulate medical imaging. There's a term for medical imaging called DICOM, and I'll talk a little bit more about that in a minute. 3JS is a 3D rendering library that we use as we want to manipulate a 3D space for an image and then render vessel trees around the heart. And then on the back end, we're using Node and Python, as well as hosting everything in Docker and AWS, very, very common technology set. All right, so the title is very complicated. So let me unpack it, tell you a little bit about what the problem we were trying to solve was. We're trying to solve a couple of problems. One is, how do we do three-dimensional viewing of one of these medical images in multiple planes in real time in the web browser? And that comes with its own bit of baggage, because that three-dimensional image space has a huge payload size. Depending upon the resolution of the image set, once we turn that into PNG files or to any kind of image file that can be downloaded by a browser, you could have hundreds and hundreds of megabytes of data. In addition to rendering all that so that a person can view it, we also want to enable real-time editing and annotation on top of that, with recalculation of downstream effects as you edit. And then we want you to be able to save your work as you go. It's a pretty complicated problem. I'm pretty excited to talk through it. So the graphic here is meant to acknowledge that there's a multi-image view where a person can be clicking on any one of these images, and as they're scrolling through any one of them, our idea is to have a person scrolling through all of them in real time, as well as annotating any one of them. And then we want to minimize traffic to the cloud. So the other part of the title is multiplanar reformat views. And what are those? Well, I thought I'd dedicate a slide directly to that so that you can have a clear picture. Right here, the two pictures on the screen represent a straightened view of an artery that's on a person's heart. And that means we took the picture all of the image data that we had in 3D space, and then we're able to calculate a brand new image that didn't exist before and straighten that artery as if we laid it out on a table. Not only were we able to do that, but on top of that, we've shown all of the annotation tools in a set of palettes so that we can represent segments of that artery, blockages in that artery, narrowing of the vessel, where the walls of that vessel are. And then a person can edit it. And if they edit it, we need to update both of these views, which are computed views in real time. I think that helps to kind of articulate what a multiplanar reformat view is and what the tool set on top of it looks like. All right. So let's talk about the journey, how we started, and then how we solved some of the problems along the way. Where did we start? Well, we started kind of in the same place everybody does when they build a web application, like a progressive web application. They start by building a server, the server-side application, which has a whole bunch of services, whether it's a monolith or a set of microservices. And they consolidate all of your application logic on the server to start, and then render everything in the web. That means that when we render the screen, but as I show here, or we make an edit, we have to make a round trip to the API, to the server. And in this example, what I'm trying to show is that the person's trying to edit the center of a vessel. They're looking down at the vessel in a slice. Then they're going to make an edit to say, actually, the middle of that vessel is in this other location. And then we have to make an API call to the server. Then that server needs to recalculate every other view on the page, as well as all the statistical analyses that go with it, using a multi-stage machine learning pipeline. Then re-render all the images, and then all the images have to reload. So you can imagine there's a whole bunch of downstream lazy loading that has to occur. That is highly prohibitive for real-time editing. All right. So what were those barriers? Now, I went through the barriers a second ago, but I really want to accentuate them because they're super important because we tackle each one of them as we try to solve the problem. The first barrier is the round trip time. Well, we have multiple stages of machine learning algorithms that are used to do the analysis on incoming imagery, and that incoming imagery is in a format that's not renderable in the web. So we have to take in the imagery, then we have to take in the edit, or we have to take in any change from the user. Then we have to run a multi-stage pipeline, and that can take 20 to 30 seconds depending upon what kind of edit it was. Then we have to recalculate the images. Then we have to make those images available for loading in a lazy load style. And we have to send a message back to the client telling them about these new messages and that they have to go and fetch them in atomic network calls. That's really a struggle. And then the payload sizes are huge. I alluded to this before, but our system uses something called the DICOM standard to ingest data from a hospital system or an imaging center where a person's actually getting the scan of their heart. And that payload is representative of a 3D pixel space. And it doesn't lend itself to a compatible format for the web, which means we have to transfer that into something we can render, like a PNG or a JPEG. And then we have to transmit all of that to the client. We started by saying, let's slice it into what we call axial slices. Those are the slices like looking down on it all the way through. So there's like, let's say there's 300 slices in a common series, a common picture set of the heart. If we lazy load each one of those, plus all the other rendered views, we get to a very high performance problem, which I can give you statistics on in a minute or two. And then users edit naturally way too frequently for any of the things I just described before. All right, so the solution, how did we unlock real-time editing capability? We did it incrementally, and I'll tackle each part individually so you can understand some of the parts that went into this. And I was really impressed with the team here when I joined, because as a disclaimer, the two other people in the room here are the people that actually built this, and I'm just getting to present it today. All right. So the part one of the solution is to drive down the amount of network calls and the payload sizes. And how do we do it? Well, when we take in that massive DICOM series, we are now, instead of transmitting every slice of the heart individually, we're compressing those into a known number of PNGs that are compressed and in 16-bit grayscale. So each PNG file has multiple slices of the image, the multiple slices of the heart. And then we decode those on the client back into their constituent parts, and then build a kind of in-memory multi-dimensional array of those pixels that we can then operate on. And that unlocks a huge amount of capability. I'll jump to that in a minute. What I really want to focus on right here, though, is by packaging up multiple slices, we drove down network calls significantly. In fact, we got to a point where we were at about 35 network calls consistently. And we drove down overall payload sizes by 30 to 50%. And I have some really cool statistics on that in just a second. All right, so here, the red in this graphic here, you'll see that we have a table. And the table, the red line is where we started. And you may say to yourself, like, why is that bigger than the first line of raw DICOM? Well, as I mentioned before, we can't actually render DICOM imagery that comes out of a health system or an imaging center. We have to transfer that into PNG format. And if we do it slice by slice, it takes what used to be 145 megs of data and turns it into 242 images of data, because we have to build the slices for all the views on the server. So like, let's say we want to build the axial slices, those top-down views, but then we also want to look on two different sides. We have to build all those images on the server and then lazy load them. So it ended up being around 1,300 network requests just to render a full picture of the heart with all the slices. And we lazy loaded all of them. So you never know when it's going to be done. In the end, we were able to drive that entire payload down into 35 network calls that very consistently on a common network connection can take about 8 seconds. And we drove down the network transfer amount, the actual payload size, to a cumulative 75 megs, which is about 30% of the size of the original payload. That was a huge unlocker for us when it came to predictability in the user experience. Now we can provide a really nice loading experience and know that it's going to finish in a certain amount of time, and take that time to display the progress to the user while we're compiling everything. And then once all the images are there, everything is client-side, which means everything can happen immediately. So I'll walk through that with one more slide. So view rendering. I talked a little bit about the networking before. Now let's talk about how we actually are rendering everything as we go. So we got everything on those 35 files. We've now decoded each batch in a web worker so that we can turn them back into the slices. And then we built a very large 3-dimensional array. That 3-dimensional array is just a 3-dimensional array of pixels, which means we can now on the client slice it in any plane we want at any slice we want and show it. Or we can generate a computed view like one of these multiplanar reformat views using purely client-side algorithms to straighten out the image. So we were able to, let me look at my notes to make sure I say it right, but basically we were able to take and do 2D to 3D to 2D coordinate transformation directly on the client once we know where the vessels are. This is extremely impactful for responsiveness in an editing framework, because now all we have to do is round trip in JavaScript in the browser when we want to make a calculation to re-render downstream. So we can handle it all in React in Redux. All right. So we solved the networking problem and got all the data client side. What did we do next? Well, now we had to take a couple of our server side algorithms, like a couple of really complex things that were tailored for microservices and tailored for a multi-stage pipeline and not response time or immediate return, and put them into the client and optimize them for speed. Additionally, we were able to start doing new things that we could never have done on the server, like building new algorithms that allow us to render any 360 degree, any degree view out of 360 degrees of an image. We can now generate something along anywhere around the edge. So in particular, we had to take some of our center line algorithms. So for example, where is the center of a vessel? And that's built into our machine learning pipeline, but we also have to rebuild that algorithm and optimize it for speed on the client in JavaScript or in TypeScript. And we did that. And the trade-off for that is that it comes with tech debt. Now we have a algorithm on the server and the client that have to stay in sync. But the price that you pay for that pays off significantly in the user experience, because we now have a user experience that's way more sticky and way more functional for a user. All right, I'm gonna jump forward now to the third part of the solution, which is how do we enable, so we've got real-time editing here happening. We've got we've got reasonable payload size over the wire. We've got all the data on the client, and we've got to figure out now how to save as we go, but not block on the UI. And that leads us to the third part of our implementation, the third thing that we did. We ended up building a really simple, but really effective request message handler on the client that allowed us to always be blocking more API requests if there's one in flight. So very simple kind of mutex driven promise return pattern here, where everybody's editing. Those messages are always being shuttled off on a client side message event, broadcast out to the browser for listeners. One of the listeners happens to be an algorithm that lets the UI refresh, and another one of the listeners happens to be the thing that would intercept and send to the server. And if there's already a post happening from a previous edit, it just queues all of those up into a merged data transfer object or model to go over the wire. And then finally, when a response comes on the next edit, then we finally submit. So that means we could have like 20 different actions in this one merged edit. But the first edit will go atomically. So now we're able to be highly responsive to users' edits, be calculating and re-rendering on the fly because it's all done on the client, and then be batching and sending all of those edits as we go. One of the tricks here ultimately was having the API have a dynamic enough ingestion pipeline that we can handle any number of edits in a batch and then apply them all to the machine learning pipeline and the recalculation pipeline, even if they may affect each other. So we had to do a lot of work in the API there as well to handle that. And those three things, which I was able to go through in about, I think now 15 or 17 minutes, have drastically improved the overall usability of this application and unlocked features that literally we could never have done with server-side rendering or calculation, including the rendering of either three-dimensional views or straightened views at any aspect of the heart or that pixel space. Before we jump to any more Q&A, I will point out there were things we tried along the way that didn't work. Now you saw, I'll address them in the opposite order. We've got web workers and WebAssembly that we've been working with and we tried. So I'll say web workers. You saw earlier, we're using a web worker, and we're using a web worker to decode the incoming PNGs and get the slices out of it. So I'm sure you may be asking, like, well, why aren't you using web workers more? Why aren't you using web workers to do all your image rendering? Or did you try that? Or are you doing that? And the answer is we did try that, and it kind of utterly failed at the time. And it failed primarily because of memory constraint issues. So that 3D multi-dimensional array that we're using with pixel data is really big when it's completely created. So copying it into another thread and also and then trying to manipulate it in that thread increased latency on the client, as well as let us hit memory caps depending upon a person's machine or the browser's memory constraints for web workers. What we found was that web workers are really great when the data is coming in batches, and we're trying to decode batches of slices for those 35 requests, as long as we peel off and do one batch at a time. Highly predictable, we can scale based upon the cores on this person's machine. But image rendering was significantly more stable when we did everything in the main thread. WebAssembly. We also worked with WebAssembly. We did a full prototype on WebAssembly and found that it ultimately had the same kind of copying problem that web workers do when you have that massive amount of data. Transferring data into the WebAssembly as you kind of marshaled across the memory boundary into that assembly took something that would be sub 10 milliseconds in the main thread and drove it up 2 orders of magnitude, or an order of magnitude to, I guess, like 1 order of magnitude to 400, 500 milliseconds. And that kind of defeats the purpose. Now, I think we know that we need to revisit WebAssembly and leverage it more. And so it's definitely on our architecture roadmap to go back and find better uses for it. But in our initial stabs, those were limitations that I think are also really well documented in literature on the web, that transferring data in and out of WebAssemblies, especially when you're operating on a large memory set in the browser, can be a prohibitive in a barrier to entry. So those are a couple of things that we did that didn't work along the way. And now we have a little bit of time left. And one of the things that we might be able to do is a little bit of a demo of how our application looks today, so that we can show some of that re-rendering. And to do that, I'm actually going to let Tim share his screen, and then we can talk a little bit with some voiceover of what that looks like, so you can get a picture of what it looks like. So I'm gonna go ahead and stop sharing, and then make Tim a co-host. Hopefully I can do that. So allow. Oh man, I can't do it. Wonder if our friend, the volunteer, can make Tim a co-host. She did it. All right, cool. Thank you. I appreciate that. All right, so Tim's sharing his screen now. And you'll see that we've got a full, what we call a study loaded. And there are multiple images here where you can see there's like multiple views of different angles on the far left. And then you've got an axial view, which is that top-down view in the middle, and a 3D artery tree And you can see that Tim is using mouse scrolls to kind of rotate and go over things. So Tim, can you scroll over the axial one? We can show how we're re-rendering kind of where we're at as we go in the other views. So in a server-side rendering format, every slice here would be its own PNG. So as we tried to scroll, if it hadn't loaded yet, you'd get latency and spinner wheels on any one of these dependent ones as you had to fire off and call secondary views. But having this all on the client allows the rendering experience to be extremely smooth. What about a showing and edit? Can we show and edit as well? Awesome. So right now, Tim's going to edit the center line on an artery, and we're going to see how by moving that, we now had to do recalculation, and the other images started to update immediately. And now all of those calculations were done on his machine, and all of the statistics on the far right have refreshed in just a few seconds, when we were seeing that take 20 to 30 seconds in our overall pipeline when we made server round trips. And all the images immediately refreshed. So obviously, I'm sure the audience here isn't a set of cardiologists, so I'm not going to go into the details of what all of these items mean, but I wanted to demonstrate some of the capabilities there. All right. Let me check chat. So that's the presentation. Are there any questions that people want to throw into chat? Happy to answer them with the few minutes we have left. I think we have about 4 or 5 minutes left. Happy to talk about any other questions folks have about the technology or some of the problems along the way. Okay, I'll wait another minute or two. No. Well, if there aren't any other questions, I will say thank you very much for attending the session. We very much appreciate it. We're very happy to participate in Denver Startup Week. Thanks to Quizlet for being the sponsor of the Dev Track. And hope to see folks in person sometime in the future for a real live session where people can just raise their hand and ask a question in a room. I think that'll be a fun day. All right. With that, I think, Tim, you can unshare. And we'll probably exit since we're right nearly at time. We've got about 2 minutes left. So thank you very much.